Hi everyone, I hope you all are doing great and you all are well also. And so, welcome to today's day 9 of Array and String Mastery series at Aarush coaching classes. So, since it is day 9, so it means that we are already doing very well if you are watching this session. Why? Because learning with consistency is not easy. It doesn't come easy. But if you are at the ninth day, means you are consistent and probably your hard work is gonna pay in the same amount as well. Okay. So till yesterday, we have covered about too many variants of problems, okay, say patterns of algorithms and problems that can be asked in the interview questions, where we have learned about working with the 1D and 2D arrays and the two pointers, then the sliding window, and then the variable sliding window. Then the last class, we worked upon the advanced array transformations, where we worked upon some pre-computation kind of problems, where prefix and postfix kind of things were used, and then one problem regarding the 2D array where the rotation was involved. So these were the basic, you can see the patterns, the category of problems that can be asked in the interviews. And at the same time, I showed you all about what kind of related problems you can practice on your own as well. See, because only understanding the problem isn't enough. Only knowing about single problem isn't enough. Once you know the fundamental concept, the fundamental pattern, then you need to apply it on multiple problems which have the similar heart and soul that to the problem that you have solved already. So at the end, only practice matters. So that's why I would still suggest that whatever problems I have mentioned at the end of the lectures, in all my previous lectures, please do solve them, okay? Because only practice is gonna help you in actual interviews. You're not gonna remember anything else if you try to remember it from the memory and try to solve the problem in front of you. There is a high chance that you are gonna stuck somewhere and ultimately you are gonna give up. But instead, if you have a proper thought process, you have practiced enough, then probably you'll be able to solve it on your own. Okay. So on that point, let's work upon today's concept, which is little bit advanced and little bit more around the optimization thing. Today I'm gonna show you about the magic of binary search. That's why I've written binary search demystified and peak element mastery. So peak element is one of the question which is majorly asked, most frequently asked, but at the same time, binary, I will show you how binary search concept can be applied to solve this particular problem, though the basic requirement for binary search is not fulfilled in this particular problem. Okay, so that's why today's session is going to be very, very interesting. So please buckle up and let's start. Okay, so first let's try to understand why binary search is revolutionary. So for that, we first try to learn why do we actually need this binary search? Because if when we didn't know about binary search, what were we actually doing? So as I always say, computer science, data structures and algorithms is no rocket science. It's complete common sense. Okay. And just by using our common sense, if we want to search something from, you can say, a heap of something, okay, or collection of too many items, or some items are gathered together, how do we search? Obviously, if there are too many items kept somewhere, okay, and I want something, let's say these are all the fruits kept in an apple here, banana, mango, something, something, something. I want to find some fruit. So obviously I will check everyone. This is apple. No, I don't want. If I want banana, this is let's say a mango. Okay, and this was kiwi. Okay, this was something else. Let's say mango is here. Then you will say yes, this is mango. I will get it. So this kind of search is called as linear search, where each and every item is checked to see if this is the item I am interested in or I am searching for or not. If it is not, then I will move to the next item. I will keep moving and comparing it till I find it. Okay. So that's why it is called as linear search. To make it more intuitive, let's imagine you have a dictionary. Okay. You have a dictionary. Let's draw it. Okay. Let's say you have a dictionary. This is. This have around 1000 pages, you know. You want to find the meaning of some word starting, word like xenon. Okay, you want to find the meaning of this word. Obviously, if this dictionary is completely closed initially, and same dictionary closed. So what are you gonna do? Initially, you will start from A alphabet till B, C, D. Once you reach the X alphabet page, then you will try to see X A B, something something, X B. Then you will reach X E, and then gradually you will reach to Xenon. See, too many comparisons are gonna happen. You are gonna search through words starting with letters A to X till you reach Xenon. Yes or no? Correct? So, this is a very, very long process and this is gonna take too much time. You may not be able to comprehend it right now because you are still thinking about just a dictionary, but dictionary was a real life example. That's all it was. I will show you the scale of things where we need to search things and why this is not gonna be very much feasible. Okay, so here also, if I have the dictionary, I will be very much bored. It is gonna take too long. It is inefficient. So what I'm gonna do then? See, what is happening is obviously, if I say, if you remember how your roll numbers in most of the schools are given, है ना, alphabetical order पे मिलता है. People with double A spelling comes first, then single A, then A, B, something like that, and then from B, then C, then D, and so on. So you can see that this is alphabetical order, which I can call as sorted. Yes or no? Sort कर देते हैं किस फॉर्म में? इंक्रीजिंग ऑर्डर में सॉर्ट कर रहे होते हैं. Yes or no? This alphabetical order is also an increasing order of the alphabets. Correct? That's how things happen. So in the dictionary also same thing is happening. We have words all the way from A to Z. A to Z we have all the words. Correct? So it is already in alphabetical order, I can say some sorted order. So if it is already sorted, so what do I need to do? I am looking for Xenon. Very intuitively, I will just think of, let's say, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. Too many things. So if I have a closed book, okay, what I can do is, instead of just going random or one page after another page, I can try just opening it from the middle. Means what is one of the middle character here? There are 26 alphabets are there, correct? J is Chan, 20, half of 26 is what? Middle of 26, 13, correct? 10, 11, 12, 13, M. So let's say if I open some page where words are starting from M. So I can from here decide that all the pages before M have words starting from alphabets A to N, correct? And all the pages next to M have words starting from alphabet O to Z. The word I am looking for is starting from X. So where do I need to go further? Of course, I will move to the right hand side of the dictionary. I will say this first half of the dictionary is useless for me. Useless for me. Correct. So I can either tear it out, do whatever, but anyhow, it is not going to be useful for me. Similarly, now once I have this much part of the dictionary only, this much part is discarded, then my search space, a search window would be this much, just half. From here again, what will I do? I will go to the middle of the dictionary. Let's say R was the middle. I will be at R words, okay? I will see X. My word is starting from X. X is still coming after R, okay? Not earlier. Then again, this much part of my search space has become useless. I will discard it. And I will go where? In this part. In this part now, what I'm gonna do? Again, I will try to figure out what is the middle. Okay, let's say W was the middle. Okay, let's say W was the middle. Then I will check again. X comes after W, before W comes after. So again, S to UV will become useless for me. I will discard it. Now from W, right inside W, X comes now. In this, I will see Y is the middle. Now X comes after Y or before Y? Obviously before Y. So Z would be discarded. It is useless for me. I will come to X part. In the X also I will try to do till I reach JSON because but for now I can say I have reached to X. Okay. Further at more steps it can apply. Now I think you have got the idea. So in total to reach X in a search space of 26 characters, how many times did it take for me? First whole 26 characters, I took one comparison till the mid in the middle M was there. So one step for M plus one more step for R. Okay. From N to Z, I reached R, middle में गया था. From S to Z, I reached W plus one more step for W. Then here I reached Y plus one for Y. Then here I reached at X. Exactly. How many steps did I take? One, two, three, four, five. Five steps only. This is just simple example, okay? Here I'm taking five steps because I'm just trying to show you figuratively. Otherwise, I was going with the common sense other part, means though it is also common sense, it was applicable only because there is some order in these things. Anywhere if I am reaching, I can clearly define where to move next, either left part or the right part, because there is an order, alphabetical order is there. If it was jumbled, then I would not be able to decide where to move next or where to check next. That's why it is a better version of a common sense. If it was jumbled, no order was there, then obviously there was no better way than directly, I mean, going for the linear search one after the other. But if there is an order, then probably we can apply this kind of logic to reach there. So obviously this is very less number of comparisons to reach our desired item, okay, or desired word. If I was supposed to, I mean, use a linear search, then A to X, all the comparisons would have to be done. So that's why here you can see the magical speed difference. I know, though it is written for the bigger inputs, so I will show you later. Don't worry about the mathematics. This is just to establish the foundation of what we are learning right now, okay? So don't worry if some things, if this number is not making much sense to you, I will show you. Okay. So linear search, let's say I have 1024 items, okay. And the item I'm searching for is the last item, then I would have to do 1024 checks, okay. But because I am halving through my search space in every successive comparison, that way I would have to just do 10 checks. Magical, right? Where I mean comparatively 1024 is too big than compared to 10, you know. But if I increase the number, it will again show you the significant difference. Don't worry, it is gonna come next. So this is more like a divide and conquer, you know. Bato and then check karo, you know, उस type का. So it is a divide and conquer technique which significantly decrease the number of times I am gonna check if I have found my desired item or not. Okay. And it takes orders of log comparison only. Order of log comparatively very small to order of n. You know, or you can directly say log n is smaller than n. Okay. Mathematically. That's how we understand things. That's why I'm calling it magical. But yeah, I know I have not shown you any actual figure till now. So you may not agree with me, sir. भी magical समझ तो आ नहीं रहा, magic है नहीं. But don't worry. That's the beauty of magic. It builds slowly and suddenly you feel कुछ तो अच्छा हो गया. Something great has just happened, है ना? So don't worry, this isn't slightly faster because log in comparison to n is not slightly faster. It's exponentially faster. Okay, from 1000 steps to 10 steps only. And this is just a small number, 1000. Even if you increase it to million also, it would still be just countable number of times. Okay, so that's not improvement. That's why I'm calling it revolution in thinking and magical search. Okay, so let's move forward and try to understand it mathematically as well. Okay, so why it's so fast? Because it have the power of halving. Let's say your search space was this long, है ना, यहाँ से यहाँ तक था. In one attempt, you decreased your search space to this long only. ये half हो गया, है ना. ये अगर 1/2 था, तो ये 1 था, तो ये 1/2 हो गया. Now in next attempt, your search space would be halved again. Let's say this time you worked upon the first half, discard the second half. ये half discard किया, यहाँ पे ये half discard किया. So this is now 1/4 है. And again, let's say you discarded this half this time. Then again from here to here, you have 1/8. You have discarded again this half. You have now 1/16. More times half होता जा रहा है, correct? Now again, discard this half. You can see how significantly suddenly the search space is decreasing, है ना? ये और छोटा होता जाएगा. Now one, if I divide one multiple, if I keep dividing one multiple times by two, then again by two, then again by two, it will almost become equal to zero. Yes or no? Almost equal to zero. That's why what is being shown here. At zeroth step, your search space was around what? Just a minute. Yeah, your search space was 10 power 6, 100%. Okay. At the very first step, it got reduced to half, 50%. Second step, half of 50%, 25%. Third step, half of 12.5%. 25% is 12.5%. Then fourth step, half of 12.5 is 6.25%. इतना ही बचा. Then till from 4 till 10th step, okay, 10 power 6 has become 10 power 3 only. Okay, which is 0.1%. And at the 20th step, this 10 power 6 has reduced to only one item. Okay, if I keep halving it, okay, at the 20th step, this 10 power 6 will become 1 only, which is nothing but almost 0%. Okay, so that's the power of halving. Okay, that's why it is so fast. In only 20 steps, if I keep halving it or keep dividing in two part and working with the one part only, then from 10 power 6, it will become 1 only. That's the beauty, that's the magic, that's the logarithmic magic, you know, because this whole sequence is nothing but logarithmic sequence. Okay, I will show you, don't worry. So let's say, I mean, 2 to the, instead of directly writing 1000, if I write 1024, it won't make much difference, but this 1024 would be much convenient to work with because this is equivalent to 2 to the power 10. Okay, 2 to the power 10. So can't I say 10 power 3 is almost equivalent to 2 to the power 10? Similarly, if I do 1 million, this is 1000, है ना? ये k था. Now this is million. 10 power 6 is equivalent to how much? 2 to the power 20. Okay. 10 power 6 is equivalent to 2 to the power 20. That's how it is. Okay. And similarly, if I go to billion, so 10 power 9. And this 10 power 9 would be equal to 2 to the power 30. Okay. So that's how it is. We can represent it, so don't worry about it. Now this is just representation. Now you can see that 10 power 6 got reduced to 1 in 20 steps. 10 power 6 is equivalent to power 20. Earlier what did we see? Log of n time लेता है, correct? Logarithmic division होता है, efficiency is log of n. So if I take log of 2 to the power 20, what will I get? Because base is also 2, so I will get 20 log of 2 to the base 2 because we keep dividing into half ना, वो 2 से divide कर, that's why base is also 2. So log of a to the base b is equals to 1. ये कब होता है? When does it happen? When, if and only if a is equal to b. So here a is equal to b or not? Base and item both are 2, so that's why it will become 20 only. Okay, and that's exactly why it is 20. आई होप यू आर गेटिंग दिस मच मैथमेटिक्स. ये थोड़ा क्लास 8-9 लेवल का होता है, बट इससे ज़्यादा कुछ नहीं आता है. ठीक है, इतना ही काफ़ी होता है. सो डोंट वरी अबाउट इट. दिस वॉज अ मैथमेटिकल रिप्रेजेंटेशन. नाउ लेट मी शो यू द एक्चुअल proof. Okay, how this log n to the base 2 is coming, because you must be thinking, sir, you have just said log of n to the base 2 है ना, ऐसा आ रहा है, फॉर्मूला लगा दिया. but how is it happening? So let me just prove it to you. Okay. Now intuitive understanding क्या होता है? Let's say each comparison reduces the problem size by half, right? हर comparison क्या कर रहा था? With every successive comparison, my problem size means my search space. Problem size is nothing but my search space is getting reduced by half. Let's say first time 1 to 100 था, 1 to 1000 था, है ना? फर्स्ट स्टेप पे मेरा प्रॉब्लम स्पेस कितना आ गया? 500, 1 to 1000 हो गया. Let's say if I went to right hand side and this was completely discarded. So how many times can we have n before we get to 1? Now if the value of n is too big, then can you count it on your hands? Can you do it manually? नहीं ना. Though the answer is log n to the base 2, but let me show you how you can do it by showing you proper proof, because doing it manually would be difficult for you, correct? So let's create an equation. So let's say Tn be the time complexity for searching in an area of size n where n items are there, okay? It is represented by Tn. But what is happening then? After each step, what is happening? We do constant work of order of one for comparison, है ना? अब मैंने चेक तो किया था, though I went to middle, but I checked if my middle item is equal to target or not. Let's say I was looking for xenon. Middle was item with M. So let's say mango was there. So is mango equal to xenon? Mango equal to xenon? नहीं है ना? No. Though it is the answer is no, but I did one comparison, na? One comparison. That's why it is written there that we do constant work order of one for comparison for each step. After each step, okay, then we search in half of the array, na? After this comparison, I discarded this particular part and went in the next part from n to z. Correct? I went in that part. That's why it is written. Then we search in the half of the array. So complete array was represented by t of n. So half of array is represented by t of n by 2. Complete array was represented by t of n, then half of array is represented by t of n by 2. Okay, that's why. So that's why the equation would become t of n is equals to at one step, okay, t of n by 2 plus order of 1, because this is the constant time for the comparison, but this much problem statement is still left for us to solve. Okay, so that's why t of n will become t of n by 2 plus 1. This is nothing but a reconciliation. Don't worry about it now. Let's understand it intuitively if you don't know much about reconciliation. You know? Because at every step, we keep dividing. You know? Then if my first equation after first step will become tn equals to tn by 2 plus 1, because I'm now reduce the problem size by half, and this was the time taken to do one comparison, correct? Now this represents the time taken to solve this half of the problem, okay? Because first half we have already discarded. I mean, one of the halves we have already discarded. Only one half is what we are gonna working with, okay? So if I replace this if tn equals to tn by 2 plus 1 is my equation, now what can I write in this tn by 2's place? Obviously, in the same equation, replace this n by n by 2. So if I put replace n by n by 2, then this will become t of n by 2 divided by 1 by 2 plus 1 plus 1. Why? I just substituted the value of n by 2 here. Okay, n को भी n by 2 कर दिया था, तो ये 1 by 2 मल्टीप्लाई हो जाएगा, प्लस 1 था एंड प्रीवियस प्लस 1 एक और आ गया. ओके, सो दिस विल लुक लाइक t of n by 2 is equals to t of n by 4 plus 1, है ना? ये दिखेगा? ये सर नो, अभी ये 1 रहने देते हैं बिकॉज ऊपर का था, अभी सिर्फ रिप्रेजेंटेशन किया है, ठीक है? नाउ लेट्स सब्स्टिट्यूट इट हियर, है ना? सब्स्टिट्यूट करते हैं. सो आई कैन राइट t of n equals to this t of n would be substituted by this part, t of n by 4 plus 1, and there was one more 1, so plus 1. Okay, that's how I can write it. Now if I go to next step, So earlier it was t of n by 4 plus 1. Now t of n by 4 will be replaced by t of n by 8 plus 1. And these two ones would be here. Correct? And this division will keep happening. Okay. Keep happening till somewhere it stops. You know? So let's talk about that stopping point also. But at the same time, let's see what pattern we are generating. First time divide by 2. Second time again divide by 2, it will become n by 4. Third time again divide by 2, it will become 8. So 8 is what? 2 is to the power 1. 4 is to the power 2. 8 is to the power 3. Third time divide किया ना? First division, second division, this one is third division. Okay, that's what 8 to the power 3, 8. Similarly, let's say I kept it dividing k times, है ना? Kept it dividing so many times such that my problem size was reduced to 1 only. That's why I am stopping. Let's say I did this division k times, है ना? I don't know how many times did I need to divide it such that my problem statement would be reduced to size of 1. So let's say I'm saying I divided k times to reduce the search space or problem size टू वन है ना तो k टाइम्स किया ठीक है अब अगर सर्च स्पेस वन पे रिड्यूस हो गया देन व्हाट वाज दिस t ऑफ n डिफाइनिंग t ऑफ n वाज डिफाइनिंग प्रॉब्लम फॉर array size of n so if I am saying that I divided k times to reduce the search space to size 1 means this t of n by 2 power k is defining search space n equals to 1 को डिफाइन कर रहा है और search space 1 कर रहा है search space size 1 okay or in short n have become 1 okay ये हो रहा है मीन्स n से जो भी रिप्लेस हुआ था ये जो पूरी वैल्यू इसकी 1 हो गई है तो मोर लाइक if or in short in another way let me tell you if you are getting confused tn represents array of size n so t1 would be representing what similarly array of size 1. Yeah, exactly. So means if dividing this array or my search space k times leading to just only one item means I mean reaching is it on correct वहां तक पहुंच ही गया था reduce करते करते so leading to only one item by dividing it k times so this thing would be equivalent to t of n by 2 to the power k है ना should be equivalent to t of 1 correct if I write it like this therefore I can say that n by 2 to the power k is equal to 1 yes or no that's what we wanted to achieve है ना now to decide what is the value of k है ना means how many times have we actually divided to reduce the search space to size 1 we need to find the value of k because k was what if I divided one time to the power 1 two times to the power 2 three times to the power 3 ना 8 आया था to the power 3 k means k times divided to make the search space size 1 only. Now let's try to solve this particular equation. Now we have reached this equation. ना? यहाँ पे भी लिखा हुआ है. So base case was t1 equals to 1. Okay. Now once we have this, if you don't know how this is getting reached, don't worry. Don't worry. Let me try to solve this for you. है ना? Let's try to solve this here. N by 2 to the power k is equals to 1. So I can write it like n is equals to or if I cross multiply है ना 2 to the power k is equals to n लिख सकता हूँ okay now this is exponential and this is just n we can't solve it directly so let's take log of both sides take log of both sides what will it be getting log of 2 to the power k is equals to log of n. Now, if there is a log, then there needs to be a base value as well. What can be the base value here? So, in short, if I don't go into much of a technicality and other proofs, because we are already trying to prove something here, just try to understand because we keep dividing this search space by 2 every time. So, in short, you can just say that the base will also become 2. If we were dividing it or continue dividing it by 3, the base would have become 3 also. Na? ये भी होता है. But because we are doing it with 2, so we will put the base as 2 only. Now, let's try to apply the formula of log of a to the power b can be written as b log of a. Okay, so let's try to apply it here. So if I apply it here, then this will become k log of 2 and base was 2 also. And this was already log of n to the base 2. Now, what other formula you can apply? If you remember from earlier, what did I write? What did I write earlier on the previous page? एक formula दिया था. Log of a to the base b equals to 1 if and only if a is equals to b. Correct? So here what are we getting? We are getting log of 2 to the base 2. It is equivalent to log of a to the base b, which can be written as 1 if and only if a is equals to b. So here a and b both are 2, that's why I can write it as 1. So k multiplied by 1 is to log of n to the base 2. So can't I write k is equals to log of n to the base 2? लिख सकता हूँ? Yes or no? So if I put k is equals to log of n to the base 2, what will be happening then? है ना? So अभी क्या हुआ था? अब मैं क्या लिख सकता हूँ? ये इक्वेशन क्या आया था? This equation earlier became Tn equals to Tn by 2 to the power k plus k. Correct? K times हुआ था. Now k, the T n by 2 to power n by 2 to power k equation, we decide that the value should become 1 for this to complete, है ना? The division should halt at this particular step. So we can write that t of 1 because this value has become 1 from earlier statements. And what is the value of k? We can take it from here. So plus log of n to the base 2. Tn equals to T1 log of n to the base 2. What is the value of T1? T1 is nothing but 1. That was a base case. Means size 1 है तो 1 ही आ गया ना, एक ही comparison हो जाएगा. So 1 plus log of n to the base 2. Negligible होगा 1. Nothing. So in short, we can write it as big of log of n to the base 2. है ना? इतना टाइम ले रहा होता है. That's the whole derivation. Okay. I hope this is working for you. How we got to this point, that what this approach or how long does this approach take? So this approach takes order of log of n to the base 2 time. Okay. You can take snapshot also and we can move further. You can take 10 seconds. If you have any question, you can write in the comment. Okay. Then we'll move further. No questions? Okay, good. Great. So basic math है, घबराना नहीं, don't need to panic. Only you need to remember these two formulas. Okay. And what happens when you take log of both sides? That's also you need to remember. Okay. Now, let's move to the binary search blueprint, how it actually works. So how it actually works is there are three essential ingredients for this to work. What is the first one? Non-negotiable foundation. What is that foundation? Like dictionary pages, organized library, phone contacts, है ना? तो क्या होता है? Data should be organized. Data should be organized. Or can say sorted in some order. Sorted in ascending or descending order. Okay, so the data should be sorted. Next, boundaries, defining search space. Because let's say at the very beginning of the problem, your search space was this wide, you know. A to Z was your search space, or 1 to 100 was your search space, you know, or 1000. But after one step, your search space was discarded, you know. One half of your search space was discarded. Let's say this first half was discarded. Now you need to clearly define your boundary for the next step. Because once you discard your first half of the search space, now the boundaries of the second half of the search space would be starting from here. 500 say, M say, Z or 1000. Okay. Not their representation, but different representation. That's why. So you can say this is left boundary, this is right boundary. If you're discarding this half, then your left boundary would be starting from here. Right boundary is still the same. No change there. I know. So you need to work around these things. Next is the middle element. Because middle element is nothing but your decision point. After comparing to the middle element, then only you're deciding where which part to discard or where to move further. If you should be discarding A to M or you should be discarding M to Z because you're looking for xenon. So obviously X doesn't come before M, it comes after M. So M becomes the key decision point where you compare point at every step, which tells you exactly which direction to go. Like here, it told you that you need to move in the right hand side instead of left hand side. Left nahi jana tha. Okay. Now, so let me show you the basic pseudocode for this step by step process. क्या होता है? Start with entire array, left it at the zeroth index, right is at the last items index, which is n minus 1. Now, while left is less than equals to right, why I have written so? To check every middle item, every possible middle item. Okay, किसी को छोड़ना नहीं है, every possible middle item. Okay, now once we have our left and right, and left is less than equals to right, then we will try to find the middle. Middle का formula क्या होता है? Obviously, boundaries index का sum को divide by 2. So left plus right divide by 2. We'll optimize it later, don't worry. Okay. So left plus right divide by 2. We now found the middle index. Now check if item at mid is equals to target or not. If it is found, good enough. Okay. Good enough and you can return directly. No issues. You can return found. Otherwise, if target is smaller than the item at the middle, if target is smaller than the item at the middle, then you need to search in the left. Hai Search left means discard right hand side. Discarding means nothing. It's just that you need to means update the boundary. Okay, update the right boundary. Okay, ऐसा आप delete नहीं करते हो कुछ. So that's why it is written mid item was greater than the target item. So that's why my new boundary would be right would be mid minus 1 है ना. So ये 501 से यहाँ start होगा, otherwise 499 से start हो रहा होगा है ना, अगर इससे रहेगा तो मिड माइनस 1 मिड प्लस 1 से हो रहा होगा. ठीक है. लेट्स से इफ टारगेट वाज ग्रेटर देन योर मिड है ना, इक्वल टू था तो ये चेक कर लिया था. 3 के इक्वल टू लेस देन ग्रेटर देन. इक्वल टू पे यू हैव फाउंड इट. Less than means you are moving in the left hand side. Greater than means you are going to search in the right hand side. So here you will update your left hand side boundary. Okay, by doing what? Left equals to mid plus 1. That's what. You will keep doing it till either you have found it or this loop terminates, you know, or loop termination. Loop terminates. And once the loop is terminated means if loop ends means not found. We will know that. Let's try to observe it here as well. So let's say we had 16 elements, okay, in the sorted order. You can see 1, 3, 5, 7. This is increasing order, okay. Index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16 items are total, starting from 0th index. What are we going to do first? So my left pointer would be at 0th index. My right pointer would be at 15th index. है ना? ये हो गया. Left 0, right is n minus 1. Now while left is less than right, what I'm going to do? I'm going to find the middle. Middle कहाँ पे? Left plus right divided by 2. 0 plus 15 divided by 2. If I take the floors, it will become what? 7. So my middle is here. Middle. है ना? Middle equals to item 15. Because the index is 7. है ना? Let me write. Mid index is 7 right now. Item is 15. Now because I'm looking for 42. Okay, so I will check. Is 15 equal to 42? No. Found तो नहीं आया अभी. ये तो false है अभी. Next, I will check is target less than item at mid. So 42 less than 15 है क्या? Or 15 less than 42, whichever you thing you want to do, है ना? 42 less than mid है क्या? Which is 15? नहीं है. What will I do? 42 is greater than 15. So go to the right. Anyway, if I want to go to the right means all the items from 0th index till the 7th index are useless for me. So I will discard them by doing what? By putting my left boundary L is equals to mid plus 1, which is nothing but 7 plus 1 equals to 8. So my new boundary for left hand side would be 8. You can see 17 is at 8th index. So here I can update the indexes 8, 9, 10, 11, 12, 13, 14 and 15. You can see. है ना? So my left is here and the right is here. Okay. Now you again find the mid. So 15 plus 8, 23 divided by 2. Correct? 23 divided by 2, I will get what? 11 if I take the base. Index is 11, item is 23. So mid item is 23. Now is my target 42 less than 23? I kya? No. Means I need to go to right hand side. Correct? Go to right. Go to right will kya karenge? Left equals to again mid plus 1. So what is the mid? Mid is 11. So left would be 12. You can see here. 25 is nothing but index 12 है ना so 12 13 14 and 15 correct and the right is here. Now again take left plus right divided by 2, so 12 plus 15 how much? 27. 27 divided by 2 how much? Base would be 13, so that's why है ना how much? Yeah, exactly. So base would be 17, sorry, 12 plus 15, okay, 7 and 2, 27 divided by 2, 1 3 point something. Okay, here though it have been started with one more item. Okay, so 13th index 13 27, yeah, 27 से start होना चाहिए था. One more step it must take. Okay, so let me write it 27 29 and 31. Okay, 27th index is what? 13 है ना. 1 2 3 4, yeah. So is my 27 item यहाँ जो है mid जो है यहाँ 27 पे, yeah it is here. 27 जो है, is it greater than or smaller than 42? Obviously it is smaller than, means 42 less than 27, false है. So where do I need to go? In the right hand side only. Still go right. So mid plus 1. So if I go to mid plus 1 for my left boundary, where will I go? I will go to mid was 13 है ना. अब ये 13 हो गया था. Now 13 plus 1 is 14. So I will go to 14th index which is 29. 14 and ये 15 हो गया. Left, right is still here. Now what will I do? I will again try to find the mid. What is 14 plus 15? 29 divided by 2. Take the base, flows means. So it will become what? It will become what? 14. So now my mid is at 14th index, which is 29. Is 29 42 less than 29? No. I need to still move to right, है ना? Right गया मैं फिर से मैं right गया. So where am I right now? अगर मैं right जाता हूँ तो obviously it was then 14, then now it is 15, है ना? So at this particular position, so at step 5 I would be having 13 first item, index 15, right is already here, left is already here, है ना? Left is less than equals to right है ना, तब तक चल रहा है, तो अभी left less than equals to right है. I will try to find mid भी यहीं आएगा क्योंकि एक ही item बचा है search space में. Now what? I will check 30 target 42 less than 31. No. So I'll go to right. Right जाने क्या करना पड़ेगा? Left equals to mid plus 1. Means left would become 15 plus 1 equals to 16. Now this loop will end. Yes or no? Because left is equals to 16. Right is equals to 15. Left should be less than equals to 15. is 16 less than equals to 15 for this loop to work? नहीं, नहीं है. This loop will terminate. Once it is terminated, not found. Simple है. नहीं मिला. So total कितने steps लगे मुझे? 5 steps total. Okay. Total 5 steps is what is happening here, no? Search space empty, not found. Yeah. 4 के लिए यहाँ पे आप 5 लिख लो. Last एक और step चल रहा होगा. Okay. Now, if I were to compare it with linear search, let's say आपको 16 item थे, you had 16 items and you were trying to find 42. You will check 1, then 3, 5, and go on, going on till 31st. And you'll say, no, 42 is not present here. है ना? So, 16 attempts लगेंगे and here you are getting it done by in 15 attempts only. 5 attempts only, sorry. Okay? Now let's, because I have already told you about the time complexity, है ना? So let's try to see the implementation here. So the implementation is like this. Just a minute. Yeah. Let me update it. 16 items थे, है ना? तो वो 4+1 ऐसे कुछ था. 16 पूरे लगेंगे या 5 लग रहे होंगे, है ना? +1 पे जा रहा था अभी. लास्ट को आप मतलब मेन पे पहुंच भी गए हो, नहीं मिल रहा है, कोई बात नहीं. Okay? That's how many times the division was happening. Okay? And if you can see why I've written 15, because इसके बाद division नहीं हुआ ना already. So effective 4 steps पे ही जा रहा. Okay? 16 पे 4 आया था. If I go for 1024, then 10 steps पे ही आएगा. You don't need to do anything. 1024 is nothing but 2 to the power 10. And taking log of 2 to the power 10 to the base 2, it will become 10 only. Okay, that's what is written. Now this much. Because in bigger data, it doesn't matter much, you know. So don't worry about it. It doesn't matter much. अगर एक दो step आगे पीछे होता है, it is similar to like this. Bigger picture हम लोग देखते हैं. Okay. And this much, it is what? It is 1 billion, you know, 9 zeros are there. So it will take only 30 steps. That's why it is magical, and that's why it is called lightning fast. Lightning fast as well. Okay, let's see in the implementation. Array is given, target is given, left pointers we are putting for the array, for any array, putting left pointer, we are putting right pointer. Let marks the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's how. While left is just equals to right, just same logic I have converted into a code, nothing else. Mid equals to left plus right one. Now you must be thinking, sir, mid का formula तो ये था, left plus right and divided by 2. Why it is happening? You can see that this particular formula, the compiler will be breaking it into like this. L भी integer है, correct? L is an integer. R is also an integer. Okay, so this formula would be broken like this. First, temp में L plus R store होगा. Okay, then ये temp 1 था. Temp 2, this whole calculation will be broken in these steps. Temp 1 divided by 2. Okay, that's how it is going to be stored. But you must be thinking, if left pointer is of type integer, right pointer is also of type integer, then their sum would be stored in a temporary variable whose type is also gonna be an integer. Okay, also gonna be an integer. ये भी integer ही होगा. But what did we talk about in the very first class? Integers की limit कितनी होती है? 4 bytes. है ना? Size कितनी होती है? L की भी size 4 bytes है. R की भी size 4 bytes है. Now, are you able to identify the problem here? Let's say left was at, you can say ये काम करते करते है ना, left was here, then left was here, ऐसे करते करते left came here, है ना? अब क्या होगा? Let's say जो R की कैपेसिटी है, कैपेसिटी ऑफ R is, for R is let's say some 2000 एड्रेसेस स्टोर कर सकता है, ठीक है? ये फुल है, फुल कैपेसिटी, फुल कैपेसिटी. अब जो एल है वो कहाँ पे है? वो 1999 पे बैठा हुआ है ना? जस्ट लिटिल लेस देन. अब मैं दोनों को ऐड करूंगा तो वॉट एवर वैल्यू इज कमिंग इज गोना ओवरफ्लो 2000 और नॉट. 2000 plus 1999 It's greater than 2000 or not? 2000 was a full capacity, इससे ऊपर भर ही नहीं सकते. So this is called as overflow problem, है ना? Overflow problem. That's why instead of doing these steps, what do we try to do? We try to do it like this. Mid is equals to left plus right minus left divided by 2. Now this whole step would be broken into temp 1 is equals to first right minus left. Okay. Temp 2 is equals to temp 1 divided by 2. Temp 3 is equals to L plus temp 2, है ना? ये temp 3 मिड में चला जाएगा. Mid equals to temp 3. ये इतने steps में divide हो जाएगा. Now you can see there is not a single step where this overflow problem is happening, है ना? It is not being encountered. Why? Now if I do R minus L, so what I am doing? 2000 minus 1999, which is equal to 1, है ना? Which is it greater than 2000? नहीं है. Means it is never gonna overflow. Never gonna overflow out of capacity. Okay? नहीं होना है. अब यही मेजर step था. This was the most crucial step. If this is done, then tampon divided by 2. Again, this is gonna give smaller value. Correct? So no chance of overflow. Though L is big, but this is small है ना? तो क्या आएगा? Again, no overflow because two bigger values combinedly gives you overflow condition. One big and one small doesn't give you. Don't worry about it. And L can't be that big है ना कि वो टाइम टू के बाहर ऐड होके बाहर ही चला जाए. करेक्ट. या एग्जैक्टली बहुत छोटा ही होगा वो प्रॉपर कैपेसिटी पे आएगा. नाउ मिड just getting allocated. That's why never gonna overflow. And if you are still thinking sir ये formula it is not similar to है ना mid L plus R minus L divided by 2 is not equivalent to L plus R divided by 2. No, ऐसा नहीं है. It is equivalent. How? Let's solve this. If I take the LCM, what will be happening? Twice of L plus R minus L divided by 2. तो क्या बनेगा ये? Twice of L minus L, L. L plus R divided by 2. Isn't it equal to L plus R divided by 2 which you were using earlier? Same here. That's why. Okay. So that was a common mistake that people always do. That's why I have written code element middle equals to left plus right minus 2 divided by 2 prevents integers overflow. That's why if you use left plus right divided by 2 तो ये overflow हो जाता है. Okay, that's why. Now code element this particular part. Left less than equals to right, why do we do? Ensures we check every element है ना. जो last middle element है ensures to check search space of size 1 because if you see that from the previous slide हम कहाँ तक आ गए थे एक आइटम पे हम नैरो डाउन हो चुके थे. That's why you need to put equal to also. Some most of the time users people mostly write less than only. They miss the equal to, so that will miss the edge case. Okay, so you need to be very careful, you know. Don't put just less than. Instead, put less than and equal to. Okay, yeah. So we already know about the time complexity. We derived it. Let me reiterate. Time complexity would be big O of log of n to the base 2. Space complexity कितना होगा? As you know, we have not used any further data structure which is taking space of the order of the size of the input है ना ऐसा हो नहीं रहा है. That's why only few variables we have used. That's why order of 1 constant space आ रहा है. Okay, that's the beauty of binary search. But the only condition is the data should be sorted है ना. Sorted data पे काम करता है. Okay, I hope this is clear to you all. Now let's move to another question which is find peak element है ना. Applying binary search magic. Let me just first show the problem statement, then we will talk more about how we can approach it. So a peak element is an element that is strictly greater than its neighbors, है ना? Peak element क्या होता है? This is a peak, correct? This is called as peak. Peak is greater than greater than right point. Things in the right hand side इससे greater है. PEAK, and greater than items on left as well. Yes or no? Yeah. That's why it is called as peak. It is greater than both left and right items. Peak element is an element that is strictly greater, not equal to also, है ना? ऐसा नहीं आ रहा है कि ये आया and ये आ गया. I can't call it peak, not a peak. Okay? Because ये left के equal है ना? Let me write, draw straight. Not a peak, okay? Strictly greater होना चाहिए. Given an integer array nums, find a peak element's index and return it. You need to find the index of peak element and return it. That's all. And they're again saying, further saying, the array may contain multiple peaks, so you can return any one of them. You know. So if I have some array, let's say this is my array. Okay, 1, 2, 1, 3, 5, 6, and 4. If I were to plot it just for your visual appeal, है ना, अब मैं इसको एक्स वाई पे से प्लॉट करता हूँ स्टार्टिंग फ्रॉम हियर दिस इज जीरो है ना दिस इज वन दिस इज टू दिस इज थ्री दिस इज फोर दिस इज हाइट फाइव and this is height 6. Okay, so if I'm starting from 1, okay, so my zeroth item would be here. Okay, and this is my index, you know, height, or can say item. This is my index, zeroth index, first index, second, third, fourth, fifth, sixth, seventh, and so on. Okay, if I were to plot it, zeroth index, first, second, third, fourth, fifth, and sixth. Okay, zeroth index item is 1, so 1 plotted. First index item is 2, so 2 is plotted at this point. Second index item is 1, so this file is plotted here. Third index item is 3, so this fellow is plotted here. Okay, fourth index is 5, so 5 is looking like this. Fourth index 5. Okay, then fifth index 6. 6 is looking like this, and fifth index. Okay, and sixth item is 4. Okay, sixth index is 4, so 4 is gonna be here. Yeah, sixth index. Now if I were to connect these dots, the shape would look like up, down, keep going up, 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 and then coming down. How many peaks are there? How many peaks are there if I have plotted this data? Obviously, this is and this is the peak. है? These are the peaks. So that's why they are written. Output क्या होगा? Because we need to return the index, है ना? Index and return it. Elements index and return it. So index are 1 or 5. Either 1 index or 5 index. And the items are 2 or 4. 2 or 6, sorry. है ना? Both 2 and 6 are peaks. So I hope this must have given you proper visualization of what this question is actually asking you to solve. Correct? Now the constraints are assume nums minus 1 means all the items in the left hand side of zeroth index, which is nums minus 1 and beyond, okay, is equal to nums n. N is nothing but items after 6 index onwards, you know, yeah, n and onwards. You can say are negative infinity, मतलब बहुत ज़्यादा कम है, मतलब ये बस नीचे ही जा रहा है एंड यहाँ से बस नीचे ही जा रहा है. ओके, सो दैट यू कांट से कि यहाँ से कोई पीक बन सकता है ना. So that's what they're saying. Elements beyond bounds, okay, are negative infinity. And they're asking you to solve this in order of log of n time, which is hinting for binary search, you know? Order of log of n time, which is hinting for binary search, because this is the only algorithm that you have learned till now, which can solve things in order of log of n. That's the biggest hint. Array is not necessarily sorted. Then you must be thinking, sir, आपने अभी last question पे कहा था that for binary search to be applied, the array needs to be sorted. But here, if you must see, that's why this problem is being discussed here to show you the version of this. There is here for the peak element, there is no hard and fast rule, but you can see that the same pattern is here. What pattern is here? Whatever item you are gonna pick, you can see that you are looking for its if it is peak item or not. And what is the property of peak? Left and right both are smaller than that. And this is gonna help you make decision similar to binary search. So let's not hurry, or rush. I will show you gradually. But before that, let's focus upon the edge cases here also. What can the edge case for this kind of problems? So example 3, if there is only one item, so that item can be considered as a peak item by definition because bounds are negative infinite है ना. अब एक ही item होगा तो bounds तो negative ही जाए तो it will be a peak है ना, zeroth index. Okay, whatever item it is. Now if there are 1 2 3 4 strictly increasing है, then last item would be the peak. If all the items are in increasing order, then after the bound it is negative infinity na? And here also it is negative infinity. So last item would be the peak. Now 4 3 2 and strictly decreasing also, strictly decreasing also. So ये भी हो सकता है. So इसके beyond भी negative infinity है, इसके beyond भी negative infinity है. So the first item would be the peak. First element is peak, है ना? So these can be the edge cases. Now let's move further to understand the approach or analogy. So the analogy would be like mountain hiker analogy and insight. Let's see. You are blindfolded. Let's say you are on some mountain, है ना? आप कहीं तो चल रहे हो. You are this person, है ना? And you are blindfolded अभी के लिए on a mountain ridge. How do you find any peak? How do you find any peak? So obviously you are gonna feel. Feel is a keyword. So you will feel the slope. What kind of slope under your feet? What kind of slope under your feet? Let's say if the slope is ascending, ground is rising ahead. If you, wherever you are standing on a slope like this and you are blinded. So you can feel that the ground ahead of you is upwards. है ना? So because you want to find peak, so peak would be ahead in the forward direction. So you will walk forward. But let's say if somehow you were here, है ना? आप ऐसे थे, you are blindfolded. The ground beneath your foot was descending, है ना? ये नीचे की ओर जा रहा था, ये अभी नीचे की ओर जा रहा था. Ahead of your foot was descending. So आप क्या करोगे? Now you will move forward. Yes or no? Yes or no? So इसका मतलब ये है कि peak is behind you. That's what is written. If the slope is descending, ground falls ahead, walk backward, peak is behind. If ascending means आगे की ओर है and it is in a little rising, then walk forward to get the peak. That's completely common sense, है ना? क्या है ये? Common sense. That's what the idea is all about. And you need to repeat take making decision on this feeling till you, because every decision of yours and every taken step taken after that decision is making you or bringing you closer to the peak, है ना? Till you reach the peak. Okay, मैथमेटिकल ट्रांसलेशन क्या है? अब यहाँ पे बाइनरी सर्च का कैसा लग रहा है? Obviously now you can sense that here there is a particular condition with which you are making a decision. So इसको ऐसा कर सकते हैं. Let's say you are at some random place, है ना? And that random place is completely the because the data is not gonna be in this format. Obviously, this is for your visualization. The data is gonna be of in this format, correct? इस format में data होगा, ये data होगा, 1 2 1 3 5 6 4, है ना? So obviously you can't just start from very beginning and do things linearly. That won't work much, and especially the concept is saying order of log of n is what they're seeking for, है ना? तो क्या करोगे अभी आप? So let's say you are at some random item, or let me just put the data, same data, na? 1 2 1 3 5 6 4. 1 2 1 3 5 6 and 4. Okay, these are all the items. 0, 1, 2, 3, 4, 5, and 6 index. Okay, nums array. Let's say instead of going randomly, you picked that. I will start from middle, left and the right, and you started from middle. No, M say. Now you will try to feel the ground beneath, है ना? कैसे feel कर रहे होगे? From this item, you will compare where you are currently standing. The item is 3. You will compare if this item, है ना? ये क्या आपके right hand side का पड़ोसी है? The neighbor in the right hand side. You will compare it with this. ठीक? So if this 3 is less than 5, means what? If I plot it, it will look like you were at 3 and 5 is at some height. 3 is less than height means क्या आ रहा है ग्राउंड इज असेंडेड है ना मतलब ग्राउंड राइज अहेड है so you need to move in the forward direction. You can see this particular part. How to move in the forward direction? Because earlier your search space was from here till here. Now you are moving to the forward direction. So what are you going to do? You will put your left from here to here. Okay, you will go in the forward direction. Ascending slope होगा. इसका मीनिंग ये कि ascending slope होगा. And if say let's say it was not less than, it was greater than है ना, तो ये डिसेंडिंग स्लोप होगा. तब वो क्या करना पड़ेगा? देन यू वुड हैव टू मूव इन दिस डायरेक्शन, है ना. सो दैट्स व्हाट द टर्मिनोलॉजीज आर रिटन. असेंडिंग स्लोप defines that the item next to is higher, and if item next to is lower means descending slope, so you need to move backwards. So obviously moving forward and moving backward is doing nothing but updating the boundaries. Okay, outing the boundaries. If I am walking forward, then my new boundary would be, I mean, left would be next to mid till the right hand side. यहाँ से. If I'm moving for backwards, then my right would be kept here, and I will move backward. You know, because I'm comparing this neighbor only. You know, so if I move this direction, I have checked it already, so I can start a boundary from here. But I have not checked कि यहाँ पे क्या है ना. अभी तो इन दोनों को check किया है. That's why if I'm moving backwards, I will put my boundary here at the mid. If I'm moving backward, if you're thinking, sir, why I'm not doing mid -1, है ना, इसलिए नहीं कर रहा हूँ because I don't know about this. But here I know both about this, है ना. That's why I'm doing this. So the insight is we don't need to see the whole mountain. By always moving uphill, we are guaranteed to find the peak, correct? जहाँ पे आपको uphill है, you'll walk forward and we are guaranteed to find the peak. Okay? Now, the negative infinity boundary ensures we never walk off the edge. Obviously, after this, if I feel negative and negative, I am gonna move backwards, है ना. अगर इधर आ भी गया तो इधर भी आ गया तो इधर जाऊंगा मैं. Okay, that's why. Now, this is a genius of adaptive binary search. We use local information to make global progress, है ना. We are using only this much of the neighborhood to make decision of our next step, है ना, which is impacting my final output. So don't worry, I will now take you through the whole step and show you how I am actually finding the answers. Okay. So 1, 2, 1, 3, 5, 6, 4. Let me put it here. 1, 2, 1, 3, 5, 6, and 4 again. Okay. And the indexes are gonna be 0, 1, 2, 3, 4, 5, and 6. Nums pattern क्या है? Each answer I is greater than its neighbor, correct? Whichever answer I means peak item, okay? Peak item. Every peak item is greater than its neighbors, both neighbors. So for any position, we can determine which direction has a peak, okay? Bunny search adaptation क्या होगा? What would it be? Search space entire 0 to n-1. So left and right, okay? Decision condition. Compare the mid item with the next item, okay, and move according to the logic. So let's say mid was here. If ascending means peak must be right direction, must be in the right. If I'm ascending, you know, means my next neighbor is greater than me. 3 is less than 5 means 5 is greater than 3. So I will move in the right hand direction. How? Left equals to mid plus 1. है ना, because I already know about 5. So I will put my left here. Okay. If descending means peak must be left, so including mid and right equals to mid. Let's see अब क्या कर सकते हैं. तो एक डिसीजन ले लिया ना, एक बार फिर से इसको चेक करते हैं. अब सर्च पे 0 n-1 कीजिए, कितना हो गया? What is it now? 4 to 6 हो गया सर्च स्पेस. What is the middle now? 5 is the middle. I went to 5. If I want to fight, what I will be doing? है ना? फिर क्या करेंगे? Now what will I do? If I'm at the 5, again I will check my padosi, the next item. Is 6 less than 4? 4 less than क्या? No, it is not. Means this time ascending nahi, this time it is descending. This is getting satisfied. So peak must be in left, including mid. Correct? Mid को include करके. Why? क्योंकि मेरे को नहीं पता. I don't know about it. है ना कि इसके इधर क्या था. So I will put my right at this. Okay. Once this has happened, okay, I will again check. I will again find a bit 4 and 5. अब mid क्या होगा मेरा? 4 and 5 mid क्या होगा मेरा? 4 and 5 and mid क्या होगा मेरा? Exactly. 4 plus 5 equals to 9. So divided by 2, mid equals to 4. अभी mid को मैं 4 पे लेके आता हूँ. ठीक. Now 5 है. अब मैं again check करूंगा. 5 is less than 6. Yes. So move forward. Ascending है ना. Move forward क्या होगा? Left must be mid plus 1. So left would go where? If my mid was here, mid plus 1. So left यहाँ आ जाएगा. Now left and right as both at. Here, once you are at the single item, then you can't do anything. अब आप ये mid plus 1 का comparison नहीं कर सकते. If you both left and right are pointing at the same position. Means you need to terminate this process when left and right are equal, because you have converged to the peak, because the decisions was in such a way leading to peak item, है ना. आपको और कुछ करना नहीं था. You were not supposed to do anything else. Just keep following these decisions. They will converge the whole search space and lead you to, or can say converge to the peak only. As you can see, 6 is the peak. Left and right both are pointing at 6 only right now. So algorithm outline, what would it be? Initialize left and right, है ना, at the 0th index and n-1 index. While left is less than right, as you can see, the termination was happening at when left was equal to right. It is different than binary search condition, है ना? So don't get confused. It is according to the requirement of the situation, है ना? Because that's why we are calling it a binary search variant. Exactly. Yes. Now again finding the mid, and then we are trying to decide if it is ascending or descending, है ना? If it is in the ascending direction, then left would be updated as mid plus one. If it is in descending direction, then right equals to mid. That's all. And I showed you why I'm not writing -1. Because we are comparing mid with mid plus one only. I don't know about the previous item. So that's why I will put my right boundary to item which I know already. So I will put right at mid if I am moving in the left hand side. Okay. And once this thing is over, once the loop is terminated and a termination, we have converged to the peak. And both left and right point are pointing at the peak element. So either you can return right or left, no issues. You know? Return left now equal to right position to a peak. That's all. Okay. So the condition left less than right ensures we always have at least two elements to compare. That's what I was talking about. If your both pointers have reached to only one item, then you can't do any more comparisons. That's why you need to terminate it. And termination would be done when left is equals to right. Till left is less than right, you have two pointers pointing to two different items. Okay, that's why you always have at least two items to compare. So when they meet, we have found our peak. It was quite intuitive. That's why I was saying बहुत intuitive है, and that's how it works. So again, I think I don't need to take you through this. I have already done it here in the thought process all apart. But yeah, for the notes, you can later revisit this. Okay, or in the video, you can revisit this. Step 1 0 पे left था, and right was at the last index, which was 6 0 1 2 3 4 5 and 6, left and right, as you can see here. So first mid was at third index. Item is also 3. Sorry, item is also 3, and mid plus one item is 5. 3 less than 5, go to right. है ना. राइट कैसे किया था? लेफ्ट को मिड प्लस वन किया था. इंडेक्स वाज 4, है ना. दैट्स हाउ. So I think I have shown it already, so I don't need to repeat it. But yeah, I can show you the implementation code. I'm taking the array because we don't know about the target, so target is not here. We just need to take decision to keep moving towards the peak. Left is 0, right is the last item. While left is less than right, then we are finding the mid, and we are comparing our mid item with the next policy, next item to the middle. If it is this ascending slope, peak is to the right hand side. Ascending means my current item is less than my next item, means it is an ascending slope. So I will move in the right hand side. By doing what? Left equals to mid plus 1. Because mid and mid plus 1 both items I know about. But else it's a descending, so I know about mid only, not previous to mid. That's why I will put my right boundary to mid only, nothing else. Okay, that's how it is happening, and we'll keep doing this till it is converged to one item, means left have equals to right. Then it will terminate, terminate, and converges to the peak. Okay, that's how it is gonna happen. That's why when left is equals to right, it is terminated and converges to peak. So you can either return left or right pointer. Both would work as a peak index. Okay, no issue upon it. Now, I have already shown you about the edge cases. Single item, it can be treated as the peak because left hand side and right hand side beyond the index, actual index would be negative infinity. So it will mark as peak only. So loop doesn't run, zero ही output हो जाएगा because left is at zero and right is also at zero. Strictly increasing, last item would be the peak, 3 आ जाएगा. Strictly decreasing, first item would be the peak. Multiple peaks, either of them, finds first peak encounter. Whichever is first encounter, it will return index. All same है, any index is valid, है ना. कोई भी इंडेक्स यहाँ पे वैलिड हो जाएगा क्योंकि कहीं तो जाके कन्वर्ज होकर रुक जाएगा. So that's how. Okay. Yeah. Now what is complexity analysis? यहाँ पे क्या आ रहा है? If you look at this, what is the time complexity here for this? Same binary search का logic लग रहा है. Nothing else. Every time we are, I mean, you can see left and right update हो रहे हैं and we are keep having the search space. So it is similar to binary search, similar to binary search. In short, let me call it BS, big of log of n to the base 2. And we don't need the data to be sorted here. Sort हो जाएगा तो peak कैसे निकालोगे? Exactly, है ना? Though it will be one peak only, but not for other test cases or edge cases. Okay. Space complexity, we are using just a variables, that's why it would be constant because of one only. So here you can see the clear comparison. Time complexity log of n to the base 2. Let me write it. Okay, each iteration halves the surface space. It is happening here as well. For 1 million elements, 20 iterations would be there, you know. But for linear search, it would be 1 million iterations. So it is 500,000 times faster for large datasets. Complexity analysis, 3 variables, so that's y out of 1 only. Totally in place algorithm. This is our best solution. Okay. So this isn't just optimization, it's the difference between feasible and impossible for real world datasets. Because real world में latency matter करती है. The shorter the latency, the better the solution is, and people like your solutions. People like your product. Okay. And the more people like your product, the more money you're gonna make. That's why the efficiency matters in terms of speed. Okay. Now about the key takeaways from this session. We have understood the logarithmic speed advantage, then mathematical proof of log entry base 2 complexity. This is base 2. Mastered three essential ingredients. Okay, sorting, left boundary and right boundary and decision making. Okay, can implement bug-free binary search. Yes, understand real-world performance impact. And a lightning fast. That's why we called it logarithmic time था इसका. Then we talked about the peak element pattern. Adapted binary search to non-sorted arrays. So now you have got this ना. पहले तो सोचा था कि सिर्फ sorted पे ही लगेगा. But according to the problem, if it have some similarity, then we can try, and if it is getting solved, it is getting solved. I know who knew कैसे ही होगा, but yeah, we found the pattern, we tried to solve it, that's all. That's how things actually work. So use local slope information for global search. Quite intuitive, very very intuitive the solution was. Yes or no? What do you think? कोई rocket science चाहिए solution के लिए? नहीं. We thought about the real life situation decision making of a human, and we just converted it into the code. We found that it is similar to binary search. We called के binary search लग सकता है. That's all. So I handled all edge cases professionally. I showed you all edge cases. achieved optimal log and time complexity. Mental framework क्या होना चाहिए ऐसे problems के लिए? Because you might get different problems. So first you need to identify, can the problem be solved by halving search space? हो सकता है क्या? Because that is the main point of applying the binary search logic, either to find the peak element or apply the binary search directly. Next, adapt. What is the decision condition? I mean, if you're having it, okay, then which direction to move, how to decide. That decision making need to be clear about, then implement to the code by managing the boundaries carefully. Okay. Next, once your basic solution is over, now you can work with the test cases. Sorry, edge cases. Okay. Test with edge cases. So that's how the whole mental framework for the problem solving works. Now, practice and next steps. So immediate practice, I will say, try to implement it on your own at least 3 times from scratch. This will give you a speed faster, make your speed faster. Solve find peak element with different test cases on your own. Run both algorithms manually. एक step run करो. That will give you clarity what is happening actually at each step. While I am doing it, will you will feel like yes, it is easy, very easy and done. But once you are trying to do it on the ID, you will try to write the code. If you get stuck somewhere, you'll not be able to figure out your galti kya hai because you don't know how to drive in things. Then gives you confidence in showing what is actually happening at every step. If you drive your code line by line, word by word, then it happens. And for the beginners or for the people who wants clarity in debugging, this should be having a habit of doing the drive manually. Okay, so do it. Now, deepen understanding, explain both algorithms to someone with some analogy. Time yourself implementing them so that you can do things faster and you can try to create your own test cases as well. Okay, next. Tomorrow, because that was the agenda that we have covered for this particular session. So for tomorrow, we'll be working more around advanced binary search and applications. Okay, search in rotated and sorted array. We will see. It is also another version of unsorted array. Okay, but because we are calling it sorted and rotated array, okay, so obviously there is some hint. So we will try to see how we can solve these things. And next would be the woodcutter problem. This one comes under abstract binary search. Abstract is a keyword here. You won't get to understand directly क्या binary search लग रहा है. But somehow once you dig deeper, you will find that yes, I am able to apply the binary search. So these are two most interesting questions in terms of patterns also, around which most of the questions are asked in the interviews. So probably this will be very much helpful for your placement preparation journey as well. Okay, so that would be all for today in terms of covering people. So if these sessions are really helping you, making much sense for you in a meaningful way, then please like, share, and subscribe, and stay tuned for our next video. That would be all for today. Thank you, everyone. Happy learning.